Welcome, everyone. Today we're diving into a detailed overview of something literally right beneath our feet, but, something we almost never think about. We're going to explore one of the wildest paradoxes of industrial agriculture here in 2026. Picture this. We have reached absolutely unprecedented heights in farming technology, yet we're somehow hovering right on the brink of ecological collapse. It's a massive contradiction. But today, we're going to unpack how the solution to this hidden crisis might actually be hiding in the waste of a plant humanity has utilized for millennia. Okay, let's just jump right in and look at the facts.
Section 1. The crisis of sterile soils. Let's take a look at the stark contrast between what we see on the surface and the completely silent reality underground. So, from a bird's eye view, modern industrial fields, they look absolutely perfect. You've got these endless, lush green rows that give off this fantastic illusion of total health. But beneath that greenery, there is total silence. Over the last 70 years or so, heavily relying on synthetic nitrogen fertilizers and herbicides has basically turned our soils into dead chemical deserts. See, synthetic fertilizers act a lot like a salt solution. They dissolve incredibly fast, the plant sucks them up, but they do absolutely nothing to support the microorganisms down there. The microbiome literally just starves and dies from the chemical stress. We are essentially growing our crops in dead dirt. So how on earth do we bring that life back?
Section 2. The architecture of hemp biochar. To really understand this, we need to zoom all the way down to the microscopic level to see an architectural marvel born right out of agricultural waste.
So what exactly is biochar? First off, actually, scratch the idea that it's just leftover ash from a campfire. It is definitely not that. It's a highly porous, incredibly carbon-rich framework. We created by heating organic biomass at super high temperatures, like 400 to 700 degrees Celsius, but crucially, without oxygen. That process is called pyrolysis. And during pyrolysis, the organic matter doesn't burn away. It transforms. It becomes a permanent, highly durable physical architecture. The big takeaway here is that this carbon framework acts as the perfect physical shelter, a literal underground bunker where beneficial bacteria and fungi can safely hide out from drought, heat, and toxins.
Now you might be wondering, why hemp? Well, people have used wood biochar for a long time, but it's pretty dense, honestly. Hemp stalk biochar, specifically from the Glacier strain, is a whole different animal. It has this brilliantly unique evolutionary structure where its surface area reaches up to 400 square meters per single gram. Just let that sink in for a second. One tiny gram has the surface area of an entire football field. It's packed with macropores and can hold up to 50% of its own weight in moisture. It's like a super sponge. This makes it the ultimate microscopic metropolis, vastly outperforming traditional wood biochar as a high-capacity bunker for colonizing soil.
Section 3. Awakening the underground microbiome. Let's move to the next phase and see how this architectural bunker sparks a massive symbiotic revolution.
The biological mechanism here is just brilliant. It happens in 4 exact steps. Step 1. When hemp biochar goes into the soil, the plant roots start releasing chemical exudates. Think of them as chemical signals and sugars. Step 2. Microbes catch that signal and just massively colonize the pores of the biochar. Now that they have a secure home, the nitrogen-fixing bacteria and mycorrhizal fungi get straight to work. Step 3. They actively release organic acids that literally dissolve the surrounding minerals. And here's the magic. Step 4. Phosphorus, which has been trapped in the soil in this unavailable dead form for years, is finally unlocked. It turns into an all-natural, accessible food source, and the plants and microbes just start feeding each other.
Section 4. The timeline of soil restoration. To grasp the sheer speed of this recovery, we can actually look at real-time 2026 sensor data tracking the soil as it wakes up.
This sequence isn't just some theoretical model, folks. This is exactly what the soil physically does, recorded by IoT sensors. Within just the first 2 weeks, the microorganisms wake up and we see microbial respiration absolutely spike by 300%. It's incredible. By weeks 3 and 4, mycorrhizal fungi start shooting their intricate networks right through the dirt. Moving into the second month, weeks 5 through 8, bacteria are pulling nitrogen from the air so efficiently that natural ammonia levels shoot up by 200%. And by the third month, the soil's physical structure actually peaks. It becomes loose, breathable, and holds water beautifully. Witnessing this exponential growth of biological activity over just 3 months is truly thrilling.
If you're a numbers person, the 2025 Washington State University data paints a really clear, objective picture. When you compare soil treated with biochar against soil treated with synthetic fertilizers, the difference is night and day.
Microbial respiration with biochar jumps all the way up to 0.60 milligrams per gram a day, whereas with synthetics, it stalls out at a mere 0.18. The available phosphorus levels are considerably higher, jumping up to 12.8, and water infiltration, which is absolutely crucial for absorbing rain and stopping floods, increases to 3.5 centimeters per hour. The data objectively proves how biochar just vastly outperforms traditional chemicals in restoring core soil functions.
Section 5, the economics of regenerative agriculture. Now, what's really interesting here is how we ground this environmental idealism in cold, hard economic reality for the farmer.
This single number is a total game changer. $176 per ton of hemp biochar. Why is that such a big deal? Well, right now, synthetic nitrogen fertilizers run anywhere from $400 to $600 a ton. And the kicker? They have to be bought and reapplied every single year, because they just wash right away in the rain. In stark contrast, a highly affordable $176 ton of biochar can treat up to 3 entire hectares, and because it's a permanent physical structure, it stays in the soil, actively working for years, even decades. For farmers, it's a massive drop in annual costs, and a brilliant shift toward long-term investment in their own land.
Section 6, the future of living ecosystems. Zooming back out to the macro level, we can clearly see the broader implications for our climate.
The crucial point here is the massive global potential. By simply recycling hemp industry waste, biomass that was literally just burned or tossed away, we can bump global crop yields by 25 to 35%. We can slash our dependence on synthetic fertilizers by 40 to 60%. But the absolute biggest takeaway for the whole planet? It's that biochar acts as a permanent carbon sink. Over a 10-year span, it has the potential to securely sequester 500 to 800 million tons of carbon dioxide right into the ground, all while creating about 100,000 new jobs in the agricultural sector. Integrating this isn't just saving farmers money, it's creating a massive, permanent solution for carbon.
To wrap up our detailed overview today, I want to leave you with a thought to chew on. What if the salvation of our soils, and really our climate, was always hiding in the waste of a plant we completely forgot about? It really makes you rethink our entire relationship with agricultural waste and the living earth, doesn't it? Thank you so much for joining me today. Keep asking the big questions, and I'll catch you in the next one.